It is important to maintain water balance or homeostasis. In order to maintain water balance, water gain or intake must equal water loss or outtake. There are several ways that we gain water. We gain water through our metabolism, and this water is called metabolic water. Examples of this are dehydration synthesis as well as aerobic cellular respiration. During aerobic cellular respiration, oxygen is the terminal electron acceptor. The electrons going through the electron transport chain bind to the oxygen as well as the protons, and this creates water. The water that we consume is dietary water. There are several ways that we lose water. During insensible water loss, we lose water through the air that we breathe out. This is the expired air. Water vaporizes out of the lungs during expiration. In addition, we also lose water across the skin as it diffuses across the skin and then evaporates. This is cutaneous transpiration. Sensible water loss includes loss through urine, feces, and sweat. Sweat is different than cutaneous transpiration since sweat is a glandular secretion. Water balance is maintained by several different mechanisms. Baroreceptors, which are mechano or stretch receptors monitoring blood pressure. Remember that the carotid sinuses and the aortic arch sinuses are baroreceptors and participate in a baroreceptor reflex. Remember that baroreceptors monitor the blood pressure, and blood pressure is directly related to plasma volume. About 90 to 93% of your plasma is water, so regulating or maintaining water balance is important for maintaining blood pressure. Water balance is also maintained by the renin-angiotensin-aldosterone mechanism, or RAS. The JG, or the granular cells, release renin when the blood pressure in the afferent arterioles decreases. Renin is an enzyme that converts a plasma protein, angiotensinogen, into angiotensin 1. Angiotensin 1 is converted into angiotensin 2 by the enzyme angiotensin converting enzyme. Angiotensin 2 goes to the adrenal cortex and causes the release of aldosterone. We'll also be looking at sodium and water reabsorption. Sodium and water reabsorption is tied to the hormones aldosterone and ADH. The fourth mechanism used to maintain water balance is the thirst mechanism. Thus far this semester, we have covered the baroreceptors, the renin-angiotensin-aldosterone mechanism, and the hormones aldosterone and ADH. In this video, we're going to be looking at water and sodium reabsorption and how they are regulated by aldosterone and ADH, as well as the thirst mechanism. Let's look at the regulation of water gain or intake. This occurs in the hypothalamus at the thirst center. There are two stimuli to the thirst center: the extracellular fluid osmolality and the plasma volume. Let's start with the extracellular fluid osmolality. Recall that solid concentration influences the osmolality. So osmolality is looking at solid concentration. The amount of water will influence the solid concentration. More water, the lower the osmolality. Less water, the higher the osmolality. So the osmolality of the extracellular fluid will increase when plasma volume decreases. In other words, when the amount of water in your plasma decreases. An increase in osmolality by about 1 to 2% is enough to stimulate the osmoreceptors in the hypothalamus. They, in turn, once stimulated, will stimulate the thirst center in the hypothalamus. This will bring about a sensation of thirst. The person then will want to take a drink. When water moistens the mouth and the throat, moves into the stomach and the intestines, and stretches those organs, this will initiate a negative feedback mechanism, turning off the thirst center. This will last for about half an hour. It is only when water is absorbed across the GI tract and moves into the blood, causing the plasma volume to return back to normal and the osmolality to return back to normal, that this is turned off. Let's look at how a drop in saliva causing a dry mouth can stimulate the thirst center.
An increase in osmolality
increases sympathetic input into the arterioles feeding the salivary glands. The arterioles feeding the salivary glands will vasoconstrict, decreasing blood flow into the capillaries, resulting in a drop in blood pressure. The formation of saliva occurs through filtration. Since filtration is dependent upon the blood pressure, there will be a decrease in filtration, leading to a decrease in saliva production, which then will result in a dry mouth and stimulate the thirst center. Let's look at the second stimulus, and this is a drop in plasma volume. Notice that the plasma volume has to drop between 5 to 10% to stimulate the thirst center. Therefore, the thirst center is much more sensitive to the osmolality, since it only has to increase by 1 to 2%. Let's follow a drop in plasma volume. When plasma volume drops, that drops the blood pressure. A drop in blood pressure in the afferent arterioles stimulates the JG or granular cells to release renin. And through the renin-angiotensin-aldosterone mechanism, angiotensin II is produced. Angiotensin II then will go to the thirst center and bring about the same response as mentioned earlier. Lastly, let's look at how we control water loss. Recall from the beginning of this video that water can be lost as insensible or sensible water loss. We're going to be looking at how we can regulate the loss. The kidneys are going to regulate water loss by regulating urine output, or what we call diuresis. There is an obligatory amount of urine that must be produced every day, and that's 500 mils. So you cannot stop the loss, the complete loss, or replace the lost water or electrolytes by the kidneys. But the kidneys can, during dehydration, support existing levels and slow down the rate of loss until water and electrolytes can be ingested. ADH, antidiuretic hormone, released by the posterior pituitary, goes to the principal cells in the collecting ducts. When it binds to the receptors there, it stimulates those cells to express aquaporins on their luminal or apical surfaces. Water moves through these aquaporins or channels by osmosis along the water gradient. Recall that the collecting ducts are surrounded by an osmotic gradient within the interstitial fluid. This gradient was created by the juxtamedullary nephrons and their loops of Henle during the countercurrent multiplier. As long as aquaporins are present, water will continue to leave the collecting duct and be reabsorbed back into the plasma. The amount of ADH released is directly related to the osmolality of the extracellular fluid. The higher the osmolality, the more ADH released. Remember, the higher the osmolality, the lower the water, or the lower the plasma volume. So as plasma volume drops more ADH will be released, therefore more water will be reabsorbed. How does aldosterone influence water reabsorption? Aldosterone goes to principal cells in the distal convoluted tubules. When aldosterone binds, it increases sodium reabsorption and potassium secretion in the distal convoluted tubules. The distal convoluted tubules are permeable to water, and therefore water will follow the sodium. As you increase the reabsorption of sodium, you will then increase water reabsorption.